And then here comes the really fancy part of Python where you can do slicing. So you would essentially slice every single element to the midpoint, and then your root.right, you will recursively slice that as well. And you would be starting not at the midpoint, because the midpoint is already taken by the root. So your root would be the midpoint. You'll be creating a new tree node, and you would be setting the value to the midpoint. So this is, in essence, what we want to do conceptually. I wouldn't get bogged down too much in the recursive syntax, but what you really want to do is every single time you're reaching a new node, you're essentially recursively creating each of the child nodes to point to a valid to another valid child node, and to another valid to the left and to its right, and you keep doing that for each subarray of the original array until you're done and you hit the base case, in which case you return none. So that when you return the root at the very end, after you've recursively called this function, you're returning each of the nodes, you're creating each node to be a tree node, and you're setting their child left and right child. So that at the very, very, very end, once you finish all these recursive calls and you return back to your this original root call, and you return root, then you automatically get this sorted array, this input array to be sorted like so as the answer. So that's what essentially the naive solution would be. We're taking these blocks and blocks of arrays, and we're finding the midpoints of each of the arrays, and then we're setting each of the nodes to be the left and the right, and so on and so forth. It's considered a naive solution because of essentially because you're traversing down the entire height of the tree, which is log of n, and then you're slicing through an array at each level. So when you take it to the extreme, what you're doing is, even though each array is divided by 2, so at each level, you find that because you're dividing 2 subarrays and each of them are divided by 2, then you'll have a time complexity of n, or you're literally slicing each level by n. And since your height is log of n, this solution is actually considered to be not as ideal or as efficient as you want it to be. So in the interest of time, what I did was essentially I made a helper function that, instead of passing in and slicing arrays and subarrays, what you can actually do is you can make a helper function, and you could just pass in the indices, the start and the end index of what you want, and then this would actually be a linear solution in terms of so it would be as good as an iterative solution. So that really shows you the power of recursion, where you can actually just let the computer and handle all the manipulations downstream, and all you really wonder more about the objects and the relationships together. So moving along to the third question, which I consider to be really where the power of recursion is really powerful, is this problem is asking, given 2 trees, can you tell if the second tree is a subtree of the original tree? So this would be it would be a huge pain to do iteratively, but luckily enough, we can find a recursive solution to this, where we would actually try to traverse through each of the nodes of the parent tree, and then we also try to traverse to see if this parent tree, the subtree, belongs to it. So you would have multiple parent trees out of the original parent tree. For example, you would have 3, 4, 5, and then you would have 4, 1, 2, and then you would have 1 and 2, and then you're trying to test each of these nodes and each of the trees that they create by themselves, and then trying to test to see if the secondary tree is equivalent to the parent tree. And so in order to do this, one way of doing this would be in terms of recursively trying to check and go down each of the subtrees, and then also try to match to see if the inner tree belongs to it. So you can see here what I did was, and this is fairly complex in terms, if this is your first time really thinking about first what DFS is and what recursion is, but this also shows you how things can really blend together and really match together, and you shouldn't really be too bogged down in terms of exactly how the stack is implemented, because once you're familiar with how recursion works, you really are abstracted away from the details and you just care more about how the relationships work out. So in essence, ignore this helper function for now and just focus on these lines of code. So what we're doing is, first, we're trying to set a base case. And if your parent tree is none, then obviously you will return false, because then if you have no parent tree, then even if your subtree is like the biggest thing in the world, your subtree is not going to be, your second tree is not going to be a subtree of the original tree. And if you find that the values of your first tree and your second tree are the same, and you recursively traverse through the subtree and you match the each node of the parent tree and the subtree, then you would return true. But if you find that these are still false in terms of this if statement, so if your recursive matching does not return true but returns false, then what you want to do is you want to keep recursively searching down the bigger parent tree, and you keep breaking down the parent tree to smaller and smaller subtrees while you're traversing, and then each of these smaller parent trees, you're trying to match the subtrees, and you're breaking down each of these each of the first tree's descendants into and you're mixing and matching with the second tree, and to determine if it is indeed a subtree, and if it is,
hi guys,
then you're returning true. So that's the that's in a nutshell. What's up, Lee? That's in a nutshell what this problem is asking. It is asking you to really think of two stacks. You're thinking in terms of the recursively traversing down the subtrees, and that's one recursive stack. And then you're also trying to recursively search each of the broken down of the original parent tree and matching it recursively with the subtree. Does that make sense? So essentially, you have two recursive stacks going on. So the one thing I like about LeetCode is that it really like some beautiful solutions that you would see, and this was like a really creative solution in terms of being more efficient than the approach we just did. And that's really creating, instead of because our solution is n times m, because what we're doing is we're mixing up essentially every single node of the parent tree. We're traversing through the second tree, so that's an n times n solution. But you can make this into a linear solution, because you could actually just traverse the first tree once and hash each of the values of its subtrees, and then all you have to do is just compare that hash value with the subtree, and then using this Merkle tree data structure, which is essentially just a tree but hashed, you're able to turn this into a linear solution. So that's like a really beautiful, like just a very elegant implementation of a Merkle tree. And people don't use Merkle trees in industry only it's used in Git and in the blockchain, and those are the only two applications in the source code where it's used. But I think this is very powerful. If you ever need to find a subtree, if you ever need to determine if a secondary tree is indeed a subtree of the original tree, to use a Merkle tree solution implementation to turn into a linear problem instead of recursively searching each of the secondary tree, you can only traverse through the parent tree, the first tree once, and then you're able to determine that the second tree is indeed a subtree. So yeah, any questions? I think I took 20 minutes exactly on the dot. I know it's a lot fast, very fast, but I think the goal is to expose everybody. And if you got lost along the way, that's fine. But it really exposed people to to recursion, to trees, and how to think about problem solving.
Edwin, question.
Yes.
So let's say, I know you could do that in a very not elegant way of coding, like for example, like printing, like each node, and then like skipping the line, and printing the each element of that list, input list. Would that be considered wrong?
Say that again. You want to?
No, in order to get the same output, right?
Mm-hmm.
In creating that list, that tree. I'm sorry. You could do like a if statement and a loop, and then at the end just printing each element of the list, and actually just printing the space and every character to actually print out that tree. That would be considered wrong. I don't know if you know what I mean.
I think you're talking more about like the cosmetic. You're just trying to print out this kind of diagram,
right?
But
you guys hear me? I'm not sure if I unmuted.
Yeah, I can hear you, Lee.
Tom, the problem is like there's two things. There's a correct solution, there's an efficient solution, and there's a clean solution.
Right.
So like what you're saying is, what if you have a correct solution that might not be either efficient or clean?
Right.
And honestly, if the tree just had these 5 nodes, then your solution would be fine. But if the tree had like 100 billion nodes, then maybe your solution doesn't take twice as long as Edwin's, or as long as like a good solution. Maybe it starts to take like 1 million times as long. And so that's why, as engineers, we try to think about how can we learn to build something efficient.
I see your point.
Yeah.
Yeah. You mean, yeah. Okay, I got it. It's just a lazy solution.
Like what you're just talking about, like printing out the tree.
Yeah. So you loop through the input list.
Yep.
And then you put it like a when you hit when you hit 2, you created a list. You created like a separate empty lists, and then at the end you just print out those lists.
Yeah,
like, or the element or whatever,
Yeah, there's a solution for this, which involves essentially that kind of trying to use the list and trying to, for example, trying to order it in such a way that you don't have to really worry too much about the actual, like recursively trying to match whether each of the original blocks of each of these groupings of the original tree is equivalent to the subtree. So there's many ways to solve this,
right,
in terms of like convert it to strings and then try to test to see if the substring is part of the bigger string. So yeah.
But I think Lee's answer was very well elaborated and clear.
Yeah, but like the thing is, you have to think about how complex would it be, right?
Right.
Yeah.
Right.
But yeah, I wouldn't be fooled by this easy difficulty. Like I think for many people, this is probably at least a medium in terms of LeetCode difficulty. So I wouldn't get too discouraged by this. But the whole goal is to show you really that recursive solutions can really make your code really clean. And you can really do these lines. You could do this all really, really beautifully. Like we didn't even have to even do this check here, or even this check here. We could have just put that if this value is equal to t dot value and is match. So what is this telling us is that essentially each of these values have to be equal to each of the first tree's values has to be equal to the second tree's values, and then we're also recursively sorting down this first tree and then also the subtree. But I think in terms mathematically speaking, it makes sense to everybody, right? That what we're doing right now is we're just breaking apart the first tree to smaller subtrees, and then we're comparing these smaller subtrees with the second tree that we're trying to test the equality condition for. That it is indeed a subtree. So this is all that this is match is doing. Breaking apart and traversing through the first tree to smaller and smaller trees and comparing it to the second tree.
Gotcha.
And if this breaking apart returns false, then all we have to do is just go to the left and go to the right of the first tree and then break apart that smaller tree. So that's all that we're doing here.
Gotcha.
Any questions about this problem or sorted array problem or the all paths problem or just trees in general? Sounds good. I'll hand it over.